Welcome back, physicists, to another day of online learning. Today we will be learning about elastic versus inelastic collisions. And as always, make sure that you have the note sheet available on Google Classroom so that you can follow along for today's lecture. So let's get started with today's do now activity. So billiard ball A of mass 0.17 kilograms moving due east with velocity of 4 meters per second strikes stationary billiard ball B, also of mass 0.175 kilograms. After the collision, ball A moves off at an angle of 30 degrees north of east with a velocity of 3.5 meters per second, and ball B moves off at some angle south of east. And we are interested in solving for the velocity of ball B. So we've seen these types of problems before. Pause the video and try to do it out. So hopefully you're getting more comfortable with solving these types of problems, but nonetheless, let's do it out together. So as always, the very first thing I'm going to do is draw out my picture. And that includes both the initial and final conditions. So initially we have ball A that's moving at 4 meters per second, hits a stationary ball B, and at the end, ball A moves off at an angle 30 degrees north of east at 3.5 meters per second, and ball B goes off south of east at an angle that we do not know at some velocity that we do not know. So our goal is to find out the velocity and the angle. So as always, we break up our momentum into an x and y equation. So here we have the mass of A times the velocity of A in the x direction plus the mass of B times its velocity in the x direction, and that's going to equal their final momenta in the x direction. So let's plug in the things that we know. Well, before we do that, they both have the same mass. So the first thing I'm going to do is I'm going to cancel out their masses just to make our lives easier with the number of calculations we have to do. So we know that the initial velocity of ball A in the x direction is 4, and ball B is stationary, so it doesn't have any initial velocity. And we have to break up our velocity into its x component, which we know is its total velocity times the cosine of the angle that it's moving at. And that is all. That's going to be added to the velocity of ball B times its angle times the cosine of the angle that it's moving at, because we are interested in the x component for both of them. So I subtract out 3.5 times cosine of 30 from both sides, subtract out that number, and we get that VB times the cosine of theta is equal to 0.968. So we have one equation and two unknowns. So we use the y equation to get our second equation. So here we have the mass of A times its velocity in the y direction plus the mass B times its velocity in the y direction, and that's going to equal their final momenta in the y direction. So hopefully this all looks familiar to you. If you're still struggling with these problems, I strongly urge you to go rewatch lecture number 3. So just as I did in the x equation, I can cancel out the masses because they are equal. And the initial velocity for both ball A and ball B is 0 in the y direction. For B, it's stationary, so there's no initial velocity. And for A, it is moving in the x direction. So now we're interested in the y component of that velocity. So we have the 3.5, the total velocity, times the sine of the angle, minus, and that minus sign comes because the ball A goes up and ball B goes down. So the move in opposite directions. So that would be VB, times the sine of theta. And VB times the sine of theta is going to be equal to 3.5 times the sine of 30, which is 1.75. So now we have our two equations with our two unknowns, and we can do that trick where we square both equations and add them together. So when we do that, we get VB squared times the cosine squared of theta is equal, or I'm sorry, plus VB squared times the sine squared of theta is equal to 0.96 squared plus 1.75 squared. And there's, so we know that if we factor out VB squared, the cosine squared theta plus sine squared of theta is equal to 1. And multiplying something by 1 doesn't change the result. And that is going to be equal to 96 squared plus 1.75 squared. We take the square root of both sides, and we get that VB is equal to 2.0 meters per second. And now we can use this to determine the angle. So I'm going to use the x equation to determine the angle. And the x equation says that VB, which we just found is 2.0, times the cosine of theta is equal to 0.968. So if we divide both sides by 2.0, we can take the cos inverse of the cosine of theta is equal to the cos inverse of 0.968 divided by 2. And we get an answer of theta is equal to 75 degrees. And we know that that is south of east because that was given to us. So we have our magnitude and we have our direction. So hopefully that looks familiar to you. And that was just a little bit of a review. So let's move on. So because it's been a little bit since I've talked to you guys over video, I want to do a quick review of the things that we've talked about before you guys did all those lab activities. So the momentum is the quantity of motion given by the mass of an object times its velocity, and it is a vector quantity that comes from that velocity. And when we deal with things in 2 dimensions, like we just saw, we have to break it up into its components. The impulse is a force acting on an object over a period of time, F delta t, and it changes an object's momentum. So that is the impulse momentum theorem, that the impulse changes an object's momentum. And we know that momentum is going to be conserved for closed isolated systems, meaning that there are no external forces acting on our system. There is no outside impulse. So we've learned this already, and today we are going to be delving into different types of collisions. Well, in order to do that, we have to study kinetic energy. We have to, so kinetic energy is the energy of an object due to its motion. We will be studying kinetic energy a lot more. That is our next unit. But for right now, the only thing you need to know about kinetic energy is that it is given by the formula 1/2 mv squared. M is the mass and v is the velocity. So 1/2 mv squared is the equation that we use to learn about the kinetic energy. And why do we need to know this? Well, we will use the kinetic energy to distinguish different types of collisions today. So let's do just that. A 2,000 kilogram car moving to the right at 20 meters per second strikes a 3,000 kilogram truck traveling to the right at 10 meters per second. The truck ends up moving at 15 meters per second after the collision. What will be the velocity of the car after the collision? So this is something you can do using conservation of momentum. Pause the video and try it out. So let's see how we would do this one out. Well, first I draw my picture. The lighter gray object is the car, and the darker gray object is our truck. We have the initial velocities for both of them, and we were given that the final velocity is 15 meters per second for the truck. And we're interested in solving for the velocity of the car at the end. So we use our conservation of momentum tools, and after we perform the algebra, plugging in our numbers, we learn that the velocity of the car is 12.5 meters per second to the right. So this part B, what is the kinetic energy before and after the collision? Well, we have our formula of 1/2 mv squared. And just like conservation of momentum, we have to apply that formula to each object in our system. So we have the kinetic energy of the car initially plus the kinetic energy of the truck initially is equal to the kinetic energy of both the car and the truck afterward, after the collision. So let's plug in our numbers. Well, we were given the masses and the velocities for all our situations, and we just found that the final velocity of the car in part A was 12.5 meters per second. So we're using that now to solve for its kinetic energy. So we plug in our numbers and we do out the algebra, and we learn that initially the car and truck have a combined kinetic energy of 550,000, excuse me, and the kinetic energy at the end is 490,000-ish. So we know that those two numbers are not equal. So where did the kinetic energy go? Well, what do the cars look like after they collide? Well, in those collisions, there is some kind of deformation, right? So here, I have this piece of paper, and I can do some work to move my piece of paper. And if I let go, it restores back to originally where it was. It took some energy for me to fold over the paper, and then that energy was then released. But if I crumple up this paper, now it took some energy to do that, I'm not going to get that energy back, right? The deformation of this piece of paper is irreversible. And much like with our car crash, there was some loss of energy due to the cars and trucks deforming a little bit. So let's look at another example. Ball A of 7 kilograms travels to the right at 4 meters per second and hits an identical ball B. If the collision causes ball B to move to the right at 4 meters per second, what is the final velocity of ball A? So pause the video and do this problem out. So let's see how we would do this problem. Well, just like we've been doing collision problems, we draw out our pictures. Ball A is this green one, ball B is the pink one. And we have our momentum equations, and we plug in what we know. Initially, ball B is stationary, so there is no momentum, and we're interested in solving for the velocity of ball A. But to our surprise, ball A stops. Well, let's study the kinetic energy of this collision. So we have our kinetic energy formula, 1/2 mv squared, and we apply that to each individual object in our system. And after doing our numbers out, we learn that the kinetic energy before is equal to the kinetic energy at the end of the collision. So what does that mean for our collision? What do the balls look like after they collide? Well, nothing is permanently deformed in this case. So mechanical energy, so the kinetic energy, is not lost. So here, this is a very similar concept to something you have all probably seen before. Now, this is called a Newton's cradle. And what's happening here is our person draws back one of the balls, and they swing out at some angle, and it looks pretty similar for both ball on the left and the ball on the right. So we do for 2 balls, and 2 balls also fly off at the end. So here the masses are the same, and those end velocities are the same, just like we saw in our problem that we just did out. So will the Newton's cradle decay over time? Meaning, will the Newton's cradle come to an end? Well, the answer is yes, right? So if no kinetic energy is being lost, then how do the balls come to rest? Well, the answer is that some kinetic energy actually is being lost. Where is it being lost? Well, if nothing's being permanently deformed, where is that energy going? Well, were you able to hear the balls colliding? Yes, we heard the clacking of the balls colliding. And sound is a form of energy. So while it wasn't lost to deforming the balls, there was a loss in energy due to the sound. Very, very minimal. Yeah, so what does that mean for our types of collisions? Well, the situation we just saw where the kinetic energy at the end, the kinetic energy before the collision does equal the kinetic energy after the collision, that is called an elastic collision. And on the flip side of that, we have an inelastic collision where the total kinetic energy before the collision does not equal the total kinetic energy after the collision. So that was in our first truck example. And we have a subset of an inelastic collision where called a totally inelastic collision, where the objects that collide stick together. So we've seen examples before, we just haven't given it a name. So there's only one object at the end, and as the name implies, the totally inelastic collision is an elastic collision. The kinetic energy before does not equal the kinetic energy after. And for all these cases, momentum is conserved. So let's do out an example. A 5 kilogram mass moving 2 meters per second east collides with a 5 kilogram mass at rest. If the collision is totally inelastic, what are the velocities of each mass after the collision? So in order to do this problem, we have to remember the definition of a totally inelastic collision. So here I have a yellow mass and I have a blue mass, and they both combine at the end in a totally inelastic collision to form this green mass. And we want to know that velocity. So we do our conservation of momentum equations, and we plug in our numbers, and we learn that the green mass has a final velocity of 1 meter per second to the right. Well, what about the kinetic energy? Well, we know that it's totally inelastic, so that the kinetic energy before should not equal the kinetic energy after. But let's just see to make sure that that is correct. So we apply our kinetic energy equations to both of our, or to all three of our objects in this system. We just solve for the final velocity of the green mass. And if we do out the numbers, we learn that 10 does not equal 5. And the reason for that is because it is an inelastic collision. So it matched our prediction, and it is indeed a totally inelastic collision. Well, let's do one more example. An archer of mass 90 kilograms shoots an arrow of mass 0.12 kilograms with an initial velocity of 73 meters per second. What is the recoil velocity of the archer? So this is an explosion problem, right? We have one mass at the end, at the beginning, an orange, mass that collides or that explodes into a yellow and red mass. Our person, 90 kilograms, and our arrow of 1.12 kilograms. So this is the exact opposite of a totally inelastic collision. So we would expect to do out this problem, we have one object at the beginning and two at the end. And we learn that the velocity of our person is 0.097 meters per second. To the left. What about the kinetic energy? Well, if it's the exact opposite of a totally inelastic collision, we expect that the initial velocity should be less than the total, or that the initial kinetic energy should be less than the total kinetic energy at the end, right? Which is the opposite of what we saw for our totally inelastic collision. So we do out our numbers, and we learn just that. We learned that there was no initial kinetic energy, and then at the end, there was kinetic energy. So where did that kinetic energy come from? Well, it came from the explosion. It came from the drawing back of the string on the bow and arrow. So we call that potential energy. It has the potential to turn into kinetic energy. And we'll be learning more about that come the next few lectures. So let's summarize. We have two main different types of collisions. We have elastic collisions and inelastic collisions. In elastic collisions, momentum is conserved and kinetic energy is also conserved. And in inelastic collisions, momentum is conserved, but kinetic energy is not. Kinetic energy is converted into heat, into sound, into deformation in some way. And then types of inelastic collisions include totally inelastic collisions, which are when the objects stick together, and explosions, which are totally inelastic collisions played in reverse, when objects break apart. And in that case, we have the release of potential energy, which increases our kinetic energy. So going forward, we have an assignment for this video lecture. Find it on Google Classroom. It's going to be due this coming Thursday, April 16th at 2 p.m. So scan the answers, send them into Google Classroom. You guys know the drill by now. And the next lecture will be coming on that Thursday after the assignment is due. So as always, I have Zoom office hours. Please email me. Please reach out if you guys want to talk about anything in regard to the labs that you guys just had, in regard to inelastic versus elastic collisions, anything about momentum. I am available. I am here, and I want to talk to you all. So as always, stay safe, stay healthy, and I will see you all soon.